Somewhere in a refinery, right now, a steel tube is quietly growing, and that growth is the last warning it will ever give. Welcome back to the channel. At Jurasa Consultation Service, we spend a lot of time thinking about the machines that never get a day off, and few work harder than the fired heater at the heart of a refinery or petrochemical plant. Tonight, the story of a single tube inside that furnace, a tube that holds back pressure, carries hot process fluid, and faces open flame, all at the same time. And we're going to watch it do something strange, slowly, permanently change shape before it ever breaks. That shape change has a name. Once you understand it, you'll never look at a bulge the same way again. Here's the setting. A fire heater burns fuel in burners. The fire lives in a box lined with refractory brick, the radiant section, where rows of steel tubes see the flame and the glowing refractory directly. The process fluid flows inside the tubes. The fire's outside. The tube wall is both the pressure boundary and the heat transfer surface. That dual role is where this story begins. Heat travels a fixed path, from flame by radiation to the tube's outer skin by conduction through the steel wall, and into the fluid. Heat only flows downhill. Every step in that chain is a resistance, and every resistance demands a temperature drop. So the tube metal is always hotter than the fluid inside it. Operators read fluid temperature easily, but it's the metal temperature, higher, harder to measure, and uneven along the tube, that decides how long the tube will live. Now add the second actor, pressure. The fluid inside is pressurized, trying to split the tube open along its length, like pressure stretching a sausage skin. The circumferential tension resisting that split is hoop stress. It grows with pressure, with diameter, and as the wall gets thinner, the dominant stress this tube will ever feel. At ordinary temperatures, this is a simple problem. Either the steel is strong enough or it isn't. Time barely matters. But raise the temperature and the rules change. As steel gets hotter, its atoms move more freely, and the stress it can safely carry falls gently at first, then steeply once you enter what engineers call the creep regime. And in the creep regime, strength is no longer just a question of how much load, it's a question of how long. Every hour the tube runs hot under pressure. It spends a little of a finite life it can never get back. That slow spending is called creep. Permanent, time-dependent deformation under a stress the tube could carry easily for a minute, but not forever. At fired heater radiant temperatures, atomic diffusion is active enough that the steel flows imperceptibly like a glacier. Engineers picture creep as a curve with 3 stages. Primary. Deformation starts quickly, then decelerates as the metalwork hardens. Secondary. A slow, steady rate, where a healthy tube spends almost its entire useful life. Then tertiary, the rate accelerates. Microscopic voids form on grain boundaries and link into microcracks. Cross-section is lost. Deformation feeds on itself and runs away toward rupture. And here's the detail that drives the rest of this story. Creep is sensitive to temperature, not linearly, but exponentially. A modest, sustained increase in metal temperature can consume a large fraction of the tube's remaining life. A tube can look fine for years, then within a single operating run start telling you it's nearly out of time. For this video, we're assuming a generic refinery-fired heater with radiant section tubes operating in the creep range, pressurized fluid inside, fuel firing outside. Real heaters, alloys, and duties vary. Every number has to come from a site-specific assessment. So why does creep make a tube bulge? Why does the diameter grow instead of the tube simply cracking? Because creep deformation is plastic flow, and plastic flow in metal essentially conserves volume. Hoop stress pulls the wall outward around the circumference. The steel responds by stretching in that hoop direction. The material has to come from somewhere, and with axial growth constrained, it comes from the wall thickness. So the tube's circumference grows, its outside diameter grows, and its wall grows thinner all at once, permanently. Understand what a bulge really is. It isn't scale, it isn't a deposit, it isn't something stuck on the tube. It is the tube's own metal, permanently strained, thinner than it was, and microscopically damaged. The tube is quite literally wearing its remaining life on the outside, where we can measure it. But not all growth tells the same story. Over years of service, every tube in the hot zone accumulates a small, roughly even diametral strain. That's uniform growth, expected aging. Gradual, predictable, trendable. A localized bulge is something else entirely. One spot, one tube, growing much faster than its neighbors. The signature of a local hotspot, and it always has a cause. A mismed or overlong flame licking the wall, multiplying local heat flux. A layer of coke or scale on the inside, insulating the wall, forcing the metal to run far hotter, even while the outlet fluid temperature looks perfectly normal. Or a tube starved of flow, removing less heat, its metal temperature climbing. This is why a local bulge gets an engineer's full attention. It says the metal right there is entering tertiary creep, the accelerating endgame. The bulge's shoulders concentrate stress. The wall beneath it is thinner, and the grain boundary voids and microcracks are concentrated exactly there. When creep tubes fail in service, it's typically an axial split right at the hot bulged location, sudden, into a firebox full of ignition sources. The good news, this failure announces itself in advance in millimeters. On the outside of the tube. If you're looking, inspection teams measure tube outside diameter at fixed, marked stations along each tube with calipers, with ply tape that converts circumference to diameter, or with laser profilometry that maps the entire surface. They map each bulge along the length and around the circumference, comparing tube to find the hot lane. A baseline measurement, taken early, makes every later reading meaningful. And the trend, the growth rate, and especially any acceleration, matters far more than any single number. Acceleration is the tertiary creep alarm. Diameter isn't the whole picture. Infrared thermography finds hotspots on operating tubes directly. Ultrasonic thickness readings quantify the local thinning. Hardness testing and field metallography, surface replication, reveal how far the internal microstructural damage has actually progressed. Shape, temperature, thickness, and microstructure. Together, they turn a bulge into evidence. So the inspection report lands on an engineer's desk. What follows is a decision ladder. First, monitoring shorter intervals between OD and thermography checks, watching the growth rate like a hawk. Second, a fitness for service assessment. A qualified engineer combines measured damage, operating history, stress, and temperature into a judgment. Can this tube keep running? And for how long? Industry frameworks exist for exactly this. The creep damage concepts of API 579, Part 10, and the remaining life concepts of API 530 for fired heater tubes. They are tools for qualified engineers, not lookup tables. And there's no universal growth percentage that condemns a tube. Anyone who quotes you one is guessing. Third, fix the cause. Burner alignment, flame pattern, flow maldistribution, internal deposits. And finally, replacement, ideally planned for a scheduled turnaround with long lead tubes ordered early. Or immediate, when growth accelerates, when cracking or leakage appears, when thinning is severe. A tube rupture in a firebox is a fire and explosion event. The conservative call is deliberate. So the next time you walk a heater row and see that gentle swelling in a glowing tube, remember what you're looking at. Not a defect added to the steel, but the steel itself spending the last of its life in the open. A warning written in the diameter. One note before we close. This video is educational only, not engineering advice, and no substitute for a qualified engineering assessment per the codes and standards applicable at your site. Real tubes and heaters vary. Real decisions require real data. Thanks for watching. Stay curious and stay safe.